Okay, we're ready for the section on gas exchange. Remember that gas exchange is the diffusion of oxygen in one direction and carbon dioxide in the opposite direction. It occurs in two places, in the lungs and in the systemic tissues. In the lungs, we're going to move oxygen from the alveolar air, dissolve it in the alveolar fluid, move it into the blood of the pulmonary capillary. We're going to move carbon dioxide out of the blood, through the alveolar air, and out of the body. In the systemic tissues, we're going to move oxygen from the blood into the tissues and carbon dioxide out of the tissues. So we have these factors that are going to regulate the concentration of oxygen and carbon dioxide. Of course, fresh air is high in oxygen, low in carbon dioxide, so with every breath you take, you're resupplying fresh air. Now, additionally, you're also humidifying the air. Remember, you can't afford to dry out your lungs, and that water vapor that you're adding is going to affect the other gases because water vapor is a gas. You're also adding carbon dioxide from the inside because every cell is metabolically active and producing carbon dioxide. So you add oxygen from the lungs, you're adding carbon dioxide from the tissues. Now let's take a brief look at atmospheric air. 79% nitrogen, almost 21% oxygen, and you can tell that adds up almost to 100 right there. We're assuming the air is dry. We kind of standardize it with as little water vapor as we can. And of course the carbon dioxide in the air, less than 1%. But remember that as you inhale this air, you're humidifying it. That is, you're adding water vapor, which is a gas. And of course, the percentage of all the gases together can't go higher than 100%. So the more water vapor you add, the lower the percentage of all the other gases. The other issue is that you never completely exchange the air in the lungs. There's always some stale air left in the lungs. So you're going to reach a sort of an equilibrium with this mixture of fresh air, water vapor from basically evaporating off your respiratory system, and the stale air that was already in your lungs. So the outset of all that is that the concentration of oxygen in the alveoli is around 13% oxygen and around 5% carbon dioxide. That's sort of the take-home message. And those gas concentrations are measured in percentages, but when we measure gases, usually we measure them with a device that measures pressure. So you need to learn to sort of equate the pressure of the gas with its concentration. And here's our second gas law, Dalton's law of partial pressures. Very simple. We love Dalton because he gave us a very easy rule. And that is to multiply the percentage of the gas times the total pressure, and that is what we call the partial pressure of that gas. So if you measure the pressure of oxygen at about 13% times 760 millimeters mercury, which is the total pressure, then you find the oxygen's partial pressure is 100 millimeters mercury. You could do the same for carbon dioxide, and you find its partial pressure is 40 millimeters of mercury. Now that's in the alveolar air. And of course that depends on the altitude. So if you go to higher altitude where the pressure is lower, you're still going to have 13% oxygen and 5% CO2, but because the total pressure is lower, then the pressure of the oxygen is lower. And if you get to really high altitude, like in an airplane where the cabin pressure is not being maintained, you can actually have oxygen diffusing backwards from the blood into the air, which will make you pass out fairly quickly. So the next time the flight attendant tells you to put your mask on before helping the person next to you, make sure you do that. You'll pass out before you can help anyone else. Now, as I said earlier, being in water can compress the air in the lungs, and that raises the total pressure. If the total pressure gets very high, if you're diving fairly deep, then you can actually get to the point where nitrogen is soluble enough in the water to be added into the blood. And then if you come up from the deeps too quickly, the nitrogen bubbles out the same way that carbon dioxide bubbles out of a carbonated beverage when you pop the top. This is the basis of decompression sickness, or the bends. So, in summary, it doesn't matter which gas it is, whether it's nitrogen, oxygen, water, or carbon dioxide. If they're a mix in a gas, in air, they all behave the same. But once you put them in water, once you dissolve these gases in the alveolar fluid or in the blood plasma, they don't behave the same anymore. Each gas has a different solubility. Carbon dioxide is the most soluble of the gases that we're looking at. Carbon dioxide is 20 times as soluble as oxygen, and oxygen is about 24 times as soluble as nitrogen. So even though nitrogen pressure is higher than oxygen or carbon dioxide, it dissolves so poorly that there's virtually no nitrogen dissolved in body fluids, and we can safely ignore the nitrogen unless you're going deep sea diving. The person that gave us this gas law is Henry. So Henry's law is the law of solubility. It determines, based on Dalton's law of partial pressure, how gases will behave when they dissolve in water. So in summary then, oxygen has high pressure, but carbon dioxide has high solubility. And because these are the two factors that we take into account, the two gases diffuse at about the same rate. Now, the 100 millimeters mercury for oxygen and 40 millimeters mercury for carbon dioxide are in alveolar air. And because the blood in the pulmonary capillaries comes to equilibrium with alveolar air, then if you measure the oxygen and carbon dioxide in the pulmonary veins leaving the lungs, it's also 100 millimeters mercury oxygen and 40 millimeters mercury of carbon dioxide. And it will stay that way, more or less, until it gets to the systemic tissues, because that's the next place gas exchange will occur. So in the tissue, cells have been using oxygen, depleting it, and producing carbon dioxide as a waste. So if you measure the oxygen and carbon dioxide in the tissue fluid, it's only about 40 millimeters mercury oxygen, and carbon dioxide pressure is up to 45. Remember, that's not very high, but the solubility of carbon dioxide helps explain that. So the difference between oxygen pressure in the lungs and oxygen pressure in the tissues is the difference between 100 and 40, which is about 60 millimeters mercury. And for carbon dioxide, it's the difference between 45 in the tissues and 40 in the lungs, a difference of 5 millimeters of mercury. That's the concentration difference, and that determines not only the direction but also the rate of diffusion. But since carbon dioxide is more soluble than oxygen, and oxygen has a higher pressure difference, those effects cancel each other out, and oxygen and carbon dioxide diffuse at about the same rate. So blood leaving the pulmonary capillaries has about the same oxygen and carbon dioxide pressures as the alveolar fluid, and blood leaving the systemic capillaries has the same oxygen and carbon dioxide pressures as the tissue fluid. So you really only have two sets of numbers to remember. Oxygenated blood has an oxygen pressure of 100 and a carbon dioxide pressure of 40. Deoxygenated blood, whether you measure it in the systemic tissues or in the systemic veins or in the right side of the heart on its way back to the lungs, that blood will have an oxygen pressure of 40 and a carbon dioxide pressure of 45.